So normal distribution it's a concept that has to do with how data is distributed. So I'll do my best to draw. It's very commonly referred to as like a bell curve. So something like this, right? Um, and it just turns out that a lot of statistical information, anytime you take data, it very often actually ends up into a form like this. Um, the general way they make a curve like this, and I'm not sure if you're familiar with histograms, but histograms are very similar to bar charts, except, and I'll try to draw it in this, they tend to make this shape here. The only difference between a bar chart and a histogram is a bar chart usually just has one piece of data, so maybe it's like, I don't know, the color red. How many people like red, or how many people like blue? I should probably change my color for that part. But a histogram actually deals with data between values, so it's more like grouped data, they would call it. You would say, like, this is from 0 to 5, so 5 people liked it, and then from here is from 5 to 10, and that's how many people are within that range. So the curve itself is actually just a whole bunch of bars that kind of end up with a general curve like this. So instead of drawing all of those, what they'll do is they just represent it as this general curve. I'll put that back. So what that means for what that means for us is that when we get information, the very first thing you want to check is that it is normally, they'll call it normally distributed. And there's actually other types of distributions. They don't tend to be as common. I'll give you just 2 quick examples down here. One of them is, yeah, go ahead.
Why do you need the data to be normally distributed?
Yeah, in order to use any of these statistical models, like the standard deviations and stuff, it has to be in this. So they may not really cover that. In fact, what it might be is they'll just go on the assumption that it's normally distributed. For instance, averages are always normally distributed. It's a very interesting thing in mathematics. They always are normally distributed. So when you have a mean of an average, it usually runs right down the middle here. There's other types of data types. They'll call it like uniform distribution, where everything is the same. It makes this rectangular thing. But these models that you're dealing with, they aren't able to evaluate that type of data. You have to use a different statistical tool for it. They'll also talk about, and maybe they've mentioned it, something that's skewed. There'll be data that's kind of skewed like that. Yeah, these models, again, we don't really focus on the tools that you're using. They actually don't deal with data like that. It only really deals with normally distributed data. Now, the bell itself can be much thinner and go like this, or it can be much, much wider, but it always kind of makes that general bell curve. That's what a normal distribution curve is. Okay, so let's take a pause right there. How do you feel about the curve here? An example of something that is normally distributed, it's a weird thing, but I should have just drew a straight line. That's way better. IQ is actually built like this. So the average human being's IQ, I believe, at like 100. And then IQ kind of goes one way or another, right? So you'll have people who have IQ between 100 and 110, and 90 and 100, okay? And then you have between 110 and 120, and 90 and 80. And then you'll see as we go a little farther along, the idea here is that there's less people under the curve. So most of the people end up in this area. So they're closest to the average in this case. And that's the key about normally distributed information, is the average is right down the middle here. So they call this the mean of the information. Have they used mu to represent it ever for you, that Greek symbol? Yeah, okay. And another thing we should talk about, we won't go too much at this point, but the difference between a population's data or a sample of data. Most likely what they're going to be doing in your case is, because you're doing case studies and stuff, they'll call it sample data, which means a population is just when you have the information about everything. So I know every human being's name in Canada, that I would have the population's information. It's unlikely I do. So what they'll do is they'll take a sample of that, and we'll take all the names from Toronto, and they'll go, okay, that's a sample of it. So the formulas end up being a little bit different. They're generally the same. But your mean, if it's population, I'll just write pop underneath. They'll use this mu. But if it's a sample, they usually use a symbol called X bar for mean.
Oh, okay.
So that's just trying to get used to some of this, the symbolism that they're going to use. So we have mean, and IQ's 100, okay? So the next thing we kind of want to talk about from there is a standard deviation. So all a standard deviation is just a portion under the curve that, and the word deviate is essentially the reason for it, it deviates from the mean. So we're at 100, so I find somebody's IQ to be at 105, okay? Well, they happen to be within one standard deviation of the mean. The deviation for IQ happens to be 10 IQ points, okay? So when they say that, a standard deviation is either plus one deviation, I should give myself more room here, or minus one standard deviation. So that means one standard deviation takes you actually from the number 90 to 110. And one standard deviation actually deals with, I don't have a good coloring thing here. It deals with 68% of the data. Okay, so 68% of all human IQs measured by IQ tests happen to fall between the IQ of 90 and 110. So that is usually something that's key to know, is how much information under a normally distributed curve. Can you see that? I don't think you can see that on that screen. Can you? Can you see the 68%?
Yeah.
Oh, you can? Okay, good. So within
so
one...
determine this?
That's just how a standard deviation works. It has... and that's how you go into the calculating of it. And I'll show you how to do the calculations. That the little formula, for instance, I'm not sure if they showed you this, but a standard deviation is like the square root of, and this stands for the sum. So you have to actually take all of your data, subtract it from the mean, square it, add them all together, and you divide by the number of pieces of data. That's what n stands for. Subtract 1, and this is for, they call sample data. This is what a standard deviation is. So you actually calculate from all your data. So it happens to be the IQ. The reason I chose IQ is it's pretty easy numbers to work with. It goes up by 10 every time for a standard deviation. But as you take your information, depending what you're measuring, a standard deviation won't always be 10. For instance, the average won't always be 100. We could be talking about salaries, and the average salary of a Canadian could be like $75,000, and then the standard deviation could be 5,223. So you end up with much uglier numbers, a little harder to work with. So that's the reason I just chose IQ, is to just get a general idea of it.
Okay, so one standard deviation away from the mean on each side. Mm-hmm. That in total is 68%, yes. Usually. Yeah. Got it.
Yeah.
Okay.
So that's the first thing we establish, is that our data is normally distributed. And then one standard deviation away, 68% of the data happens to be within that. Okay? So then you go from there. 2 deviations away. So you go 2 standard deviations away, so either positive or negative. Standard deviation. Okay? So that would be from 80 to 120. And it just so happens that this, again, is so this includes that 68, okay? And this one ends up being 97% of the information. Now, my bell curve isn't wonderful. I should have had it drop off a little more, but 97% of all of the information under the curve happens to be within 2 standard deviations. And then if you go to 3, I don't think I remember this decimal off the top of my head, but 3 standard deviations, positive direction, and the negative direction is I think it's 99.7% falls under there. 99.7%. So from here to here. So if you take IQ from 70, which is considered almost towards the end of a disability, to 130, which is considered a genius if you have an IQ there, almost the entire human population falls within that 3 standard deviations. okay? And depending on the data that you work with, those numbers will always change, but the concept of a deviation, those percentages will always stay the same. So you'll get your mean. Anything one standard deviation plus or minus, that will be 68% of your data or the people or whatever it is you're measuring. Two standard deviations will take up 97% of the data. Three standard deviations is 99.7. And that's where you start to get into, I don't know if you've talked about confidence intervals. You'll start to talk about maybe those a little later. How confident you are about data. This is around the general same idea that, we're very confident that within 3 standard deviations, you're probably going to get all of your data within there. They consider this, anything out here on the tails, to be outliers. Like, it's very, very rare that you have somebody who has a higher IQ than 130 or somebody who has a lower IQ than 70. Okay. Let's say we've written some data down. This is goals of a soccer player, hockey player, whatever you have it, over the course of a couple nights, okay? If we're talking about, first of all, just the mean or the average of something, what's neat about Excel is I can very quickly find it. I don't have to actually calculate this myself. If I hit equal an average, that pops up. So I typed in AV. Oops. AV. I'm going to actually have to select the formula. There we go. And I can just highlight the numbers I want. So very quickly, I have found the average. So this person's scoring 3 goals a night. So they'll use something like X bar to represent it, but we can say the mean is equal to 3. So the next step, if you were to calculate standard deviation, what they would want you to do, and I'll put it at the number 3 here, you would take each of these. Each of these is a piece of data, and you would subtract it from this number. And that's what this X minus X bar is. That's the idea of get a piece of data, subtract it from the mean, and then add all of those differences together. So what's good about Excel is instead of me actually having to do that, I can very quickly say, here's my data subtracted by 3 here. And then I can just copy and paste this all the way through. Oh, I jumped to the bottom. There you go. I can just paste all of this through. In fact, you can grab this little corner down here and it'll do all of that information for you. Is this something you guys have done with Excel? Yes, no, maybe?
No, but I would say I'd know how to do that in Excel a bit.
Yeah.
I guess.
Okay, so what's good about it is instead of going through that really long test, is Excel also has standard deviation. So instead of having to do all that, I can literally just highlight my data and it'll give me a standard deviation really quickly. So what this is saying here is this person gets an average of 3 goals a night and the standard deviation is 1.29. So in other words, if I was to make I can't make really a normal distribution curve here, but I'll do my best here. We'll say this is the mean. Okay, so 1 standard deviation to the right would be the number 3 plus that information, okay? So all of this person's goals are going to be between equals 3, and I'm going to subtract that. So we took a sample of their goals. Let's say it was mid-season. We took a sample of the goals they get each night, -1 ST. And what we found is, typo, yes, thank you. It's not what I wanted. ST. Why are you doing that? -1, standard deviation. I don't have a formula. No, thank you. I understand, yes. Machine. Let's try that. -1. Sorry. Thinks I'm trying to type in a formula. So what we're trying to say here is if this person we took a sample of their goals, it turns out the average is 3 goals a night. 68% of their goals, we're making the assumption that 68% of their nights, they'll either score between 1.7 and 4.3 goals. Now, obviously, you can't score a 0.3 of a goal, but that's how you start to get into messy numbers with standard deviations. The other thing that's key here is we only have 2, 4, 6, 7. That's a really small sample size. And that's where you start to get into the difference of like t-tests versus z-scores is depending on how large your sample size is, you use different charts. A t-test is for really small sample sizes where your z-scores are usually for pieces of data where you have more than 30 of something. Okay, sorry, we're kind of doing like a whole blanket overview here. So with that being said, if they were ever to ask you, well, let's say we want to calculate the probability that 97% confidence, how many goals they would get in a night. Well, I can kind of go to 2 standard deviations, and I can put that exact same formula in. 3 plus, I'm going to say 2 times what a standard deviation is. And that would be the top end of their goals. And I can do the opposite over here, and it'd probably be about 0. Let's just see quickly. 3 subtract 2 times this. Okay, so we can say with 97% confidence, okay, or we should say that 97% of their totals in a night will be between 0.5, so pretty much 0 goals, and a little over 5 goals. And then if you go to 3 standard deviations, I mean, you're in negative, so that doesn't even really make sense anymore. But this is the point of finding a standard deviation, is you're trying to capture so you can make probability predictions about things. So we can say that, oh yeah, it's probably going to be within this. They'll on average get 3, and most likely it'll be between 1.7 and 4.2. And if we want to be very conservative, we would say, most of the information will be between 0.4 and 5.5. This is sometimes used in like production with error rates, and you're trying to estimate the probability that your manufacturing is going to produce something that's going to have an error to it, or it's going to fail. You'll get an idea of it within this. So usually the information is normally distributed, and then we find what the standard deviation is. So how much does it deviate from the model that we're building, or the mold within the manufacturing plant? And then it gives you an idea of how many of your things over the course of a year will be like, faulty or malfunction or something like that. And then from there you can do like financial risk assessment. Oh, is it worth it to me to upgrade our stuff, or do we just take the hit for the couple things and reimburse those people? That's where you start to use this statistical data within the business world, at least. Is that okay-ish?
Yeah, no, that's good. So 97% of the time we would be sorry. Okay, wait. So
when they talk about a Z-score is actually referring to a normal distribution curve. And this curve, they don't talk about it, but technically everything under the curve, like all of this space, is supposed to equal 1. This happens to equal 1. They've standardized it so it equals just 1, as in like the idea of 100%. 100% of your data is under this curve here. So the mean ends up being pretty important here, because when you get a Z-score, Z-scores are looking at a piece of data subtracted by the mean divided by a standard deviation. Okay, so that's where our standard deviations are important, because it's part of this Z-score formula. So let's say we're working with IQs again, just because the numbers are a little simpler to work with. If a piece of data happens to be, let's say 125. So we found a piece of data that was an IQ of 125. We'll say that IQ is, okay? So we know that falls somewhere over here. Maybe we want to know what percentage of people have an IQ less than that, or we could do the opposite. How many people have an IQ greater than that? Or the question could be worded, what's the probability that you find somebody? In other words, like, again, that would be less than. You're looking at the less than value. You can plug it into this little formula here. So 125 subtracted by, so that was our piece of data, 125. It's subtracted by X bar. X bar is just the mean. And for IQ, it happens to be 100. And we said a standard deviation happened to be 10 with IQ. When we subtract that, we just get 25 over 10, which is 2.5. In other words, what that means is somebody's IQ that's 125 is 2.5 standard deviations positive above the mean. And if we think of percentages, okay, 1, 2, that's a really high IQ, because it's outside of 2 standard deviations, right? Since 2 standard deviations we said was 97% of all information. Another way you can look at it, and this is just an overview, it's not something you would have to calculate, but from the mean to the left, since this entire curve is equal to 1, from the left of the mean, that's 0.5 or 50% of the data. So 50% will be to the left and 50% will be to the right, okay? And if we start to know that this section is 68, and since it's even, we can actually split that number to figure out like what a column is worth. Essentially what a Z-score is giving you is what percentage is to the left of it. That's what it's going to find. And in this case, you'd find it to be, it's probably something like 98%. So it's in the 98th percentile, this IQ. It's a really, really high IQ. So that's what you're doing with Z-scores, is you're just trying to find where they fall on this normal distribution curve. So that's the purpose of looking up these charts. They don't expect people to memorize what the percentages are. Usually when you find the number, it's like 9162 or something like that, and they continuously move up. You just reference the chart for it, but it's actually just giving you a percentage. What percentage of the curve is falling to the left of it or to the right, depending on what type of Z-score or Z-chart you're looking at. We've talked about that. Then we start to find about correlation coefficients. So R is equal to the sum of, and sometimes they'll refer to it as like Zx times Zy divided by the sample minus 1. Is this a formula you've seen before for correlation coefficient?
I'm sure, but yeah.
So
this is the language.
Yeah. So what's happening now is we've talked about normal distribution and stuff. That's all one piece of data. Like for instance, when I talk about IQ, I'm only talking about one variable there. It's just the IQ. So when we're referring to it, we're just talking about one piece. When you talk about linear regression, we're on a y and an x axis, and what that is, it's two dimensions. So previously, this is all one dimensional, one variable, one concept, and we do all these funny calculations to find information about it. But as soon as we get to here, we're talking about two pieces of information, right? Because there's an x and a y. So there's some relationship. And what we're trying to find out is there correlation? They've probably talked about whether the difference between correlation and causation, just because something's correlated doesn't mean that actually causes it to happen, but it can help you find info like that. There's some great websites on the internet that talk about ridiculous correlations, like it'll be like the winning streak of a hockey team and the cheese consumption of a Scandinavian country, and they're like perfectly correlated. And it's to prove that it doesn't mean it's causation. It just means there's some kind of connection between the two. So we have two pieces of data now, and this is where standardizing data comes. So the idea is that, we have a bunch of, wish those were a bit bigger, but the idea of a scatter plot, and we want to figure out what kind of relationship this is. So we look for a line of best fit. And when we talk about lines, we actually refer back to some high school math, which is usually not what people remember, because who really tends to remember their high school math? But it's talking about linear. When they say line, they're talking about a linear equation. And a linear equation is usually written as y equals mx plus b. So y is all of the coordinates on the y-axis, and x is all of your coordinates on the x-axis. So for instance, if this is a point, this point might be 5 and 6, because this is where it is on the x-axis, and this is where it is on the y-axis. I don't know what this data is. I mean, I can make it up. It could be, like we said, a team's winning streak and how much cheese somebody's consuming. So those are what those represent. But M and B, those actually become important. And most likely you're probably seeing them like this. Y hat is equal to B1x plus B naught. Does that seem like it's familiar to you?
Is that hypothesis testing?
This is for linear regression. This is actually how to find the equation of the relationship between the two things.
Yeah, so we would have just literally
got to that. Okay, that's fine. When we do this standardizing process, the idea is we're trying to find, this is the general idea, some line that fits this data. And maybe it's this, maybe it's this. From looking at it, you could usually get a general idea that it's more one way than the other. And in this case, it's not going to be, that would be considered a negative relationship. This is a positive relationship. The reason they call it a positive relationship is if you're familiar with your quadrants, I'm going to give these, there's 4 quadrants in, it's called the Cartesian plane, this thing here, but it's just like an XY axis. So you have 4 of them. And these numbers, they both happen to be positive, okay? And when you multiply a positive by a positive, you get a positive value, all right? So this value multiplied by this value, that's exactly this concept, zx times zy. So the standardized value of x and the standardized value of y, when you multiply them, you get positive. And it just so happens this quadrant happens to be negative and negative. And when you multiply negatives, you end up with a positive value also. So as a way of trying to figure out if a relationship is positive or negative, you can actually look by how many of these dots or these pieces of data fall in this quadrant or this quadrant, and it can just give you a general idea. It won't give you the exact answer, which is most likely what you, if you have to calculate, you'll end up using this, but it'll just tell you this is a positive slope. It's going from the bottom left to the top right. And I'll use yellow. Yeah, yellow might stand out. Nope, that's terrible. Let's try red. If you have something that kind of goes down this way, that kind of gives you the idea that, okay, this has a negative relationship to it. Okay?
Okay.
So that's just the idea of positive and negative relationships. It's not, well, that's going to take a while. Not imperative to know those little tricks there, but it is important to know the idea of a positive or negative relationship, because what it means is as this variable seems to go up, this one seems to go up. That would be the positive relationship. And a negative relationship would be the opposite of it. As the X1 goes up, so maybe as a team wins, this town tends to eat less cheese. That's the only difference. It doesn't mean that one is better than the other. It's just how they interact with each other in terms of a correlation. So as this goes up, as this goes in a positive direction, this goes in a positive direction. And if it was the opposite, the curve was coming downwards. As this goes positive, this number goes negative. Just as how they relate to each other. In terms of the correlation coefficient, which I wrote it on a page. Oh yeah, it's right here. In this thing, the R value, the closer it is to 1 is the stronger it is. That means it has a really strong relationship with something. And to have a really strong relationship, it just means how tightly knit around our line of best fit are we. If all of the data is like that, where they pretty much look like they all fall on it, that means the number that you calculate for this is going to be really close to 1. It's going to be a really strong relationship. In other words, they're very closely correlated. If it's -1, that also means it's really strongly correlated. It's just that in this case, it's a negative relationship between the two of them. So as one goes positive, the other one goes negative, but it's still really, really strong because it's close to 1. Essentially, with a correlation coefficient, it's always between -1 and +1. Sorry, I tried to make a number line halfway through there, and that didn't really work out. Let's try that again. Okay, so everything happens to be between these two numbers. The closer you get to the extremes, the stronger the correlation is. It just happens to be, it looks like it's 1-to-1 or 2-to-1 or something like that. The closer you get to 0, though, the weaker the relationship is. In fact, it's possibly no relationship. So if you calculate an R value that's approximately 0, there's really no correlation between these things. In other words, the dots are so spread out that I can just throw any line around here because nothing seems to really relate to each other. So in other words, these things won't have a correlation. They don't really match or meet with each other.